In the previous class, we have seen that the output power of a continuously working laser cannot be indefinitely increased simply by increasing the power of pumping. I tried to explain to you the reason for this in the last class, but as this is an important concept, I therefore would like to explain to you this briefly so that the concept gets registered in your mind clearly. For this, let us consider that a CW laser, it is giving out an output of power 1 watt continuously in time. So if we represent it pictorially, this is time, this is power, time, and this is 1 watt. So the laser's output producing a continuous output of power 1 watt in time. Now, if you try to increase this power output by increasing the power of pumping, then initially, as you have increased the power of pumping, that means you are dissipating more energy, pump energy in time. So you will be creating more population inversion and in turn gain. Therefore, the laser would produce more output in the beginning. Suppose the laser, as a consequence of increased pumping, it gives you a higher output. But as you have increased the input energy to the lasing medium, so more energy now would stay back into the system, that you know. And because of this energy, which is eventually dissipated, it will cause more heating of the lasing medium, and as a result, the population of the lower laser level will also increase because the temperature of the gas of the lasing medium will increase. This thus in effect will reduce the population inversion. You have the upper laser level and lower laser level. If the population of lower laser level is increasing because of increased temperature, so that would reduce the population inversion and in turn the output power of the laser. So although initially the power may show a slight increase, but eventually the power tend to reduce. Of course, you can remove this extra heat which is being generated to bring down the temperature and restore the output power to a constant value, maybe at a little above this 1 watt. But there will be a limit of capacity of the heat removing mechanism of the system for the removal of the heat. So a novel concept would be to increase the power of the laser by operating it in pulsed mode. To understand this, let us consider that the laser is operating at an efficiency, pumping efficiency of 10%. That means to produce 1 watt coherent optical output, you are putting at 10% efficiency, you are putting, if we put the pump power, 10 watt pump power. So at 10% efficiency, this is giving you 1 watt of coherent optical output, of course, a directional beam of light. Now let us not worry about whether we are pumping it optically or electrically. So 10 watt pump power means in 1 second, suppose this is my 1 second, at 10 watt, 1 second, at 10 watt power at 1 second, we are dissipating 10 joule energy. So that means this is 10 watt. We are dissipating 10 joule energy in 10. So in 1 second, the laser is also producing 1 joule as its optical. Now we have said that if we try to increase this power, so from 10 joule, if we make it 15 joule, then although there may be some initial increase in the output power, but eventually power will reduce because as the more energy is being put into the system, so the fraction of energy that stays back into the system also will increase. That will eventually increase the temperature of the medium, which would reflect in reduction of population version and in turn the output power of the laser. So how can you actually increase the power of the laser without actually making a provision for removal of the extra heat that is being generated? You dump certain joule of energy in a lesser time. For example, say we put this 10 joule of energy within a time which is half second. That is, we are now putting this 10 joule of energy within half second. So then the power that we have put in, the power is now raised to from 10 watt to 20 watt. Because 10 joule of energy is now being put into half second. The power now has been increased from 10 watt to 20 watt. Now because of this that you have putting in so much more energy in half second, we will create also more population inversion and in turn the gain, and the laser also tend to produce more, give more output. So, all right, choose another color. So the laser would produce more power. Now because it is a pulse, it is being pulsed, so the energy will eventually go to zero, the energy that is being pumped in half second. The output power of the laser also would then become zero as the pumping stops after half second. Now at this point, the temperature of the medium has risen much more than what was happening in the case of continuous operation, where 10 watt power, when the pumping power was 10 watt. Now at this point, we wait for next half second, and the medium will then return to the ambient condition. And at this point, to put again 10 joule energy, to put again 10 joule energy for 10 joule energy again for half second. Half second. So we will have now the next pulse. So wait for again half second before the temperature comes back to the ambient condition. So you put again the next pulse. So you will have the next pulse and so on. So by pulsing, then you will produce train of pulses, and the peak power of the pulse will be more than the continuous power that was otherwise been possible for the laser to emit. Although the peak power has increased, but you can clearly see the average power of the laser may still remain the same as 1 watt. So you may be wondering, so why then? Why then go for all these things? Because the average power may still remain the same as 1 watt. So what is the reason? The reason is you may actually looking for some application where 1 watt power will not suffice. You need more power. But you don't need that more power continuously. You may need that increased power only for a brief period. That is where this comes handy. So you increase the output power, but over a brief period of time. And you increase this by not removing, making any provision to remove the extra heat that is being generated, removal of by removing this extra heat. You simply pulse, concentrate the energy within time, and you increase the power that is being produced by them. So, all right, I think you have now understood the concept of pulsing. How by pulsing a laser you produce more power, which otherwise would not have been possible to obtain by operating the laser in a continuous mode. So, all right. Now, the next question that we ask is, what will the maximum achievable power from a pulse laser? Can you indefinitely increase the peak power of a pulse laser? Well, to understand this, let us consider two situations where the energy is being pumped slowly and rapidly, the two situations. And this has been pictorially represented here. The top traces actually show the pump power in time. In one case, it is being pumped slowly, the other case rapidly. The middle trace, and as you pump, the population inversion and in turn the gain also will build up. The middle trace shows the temporal variation of the population inversion and gain in time, and the bottom traces show the output power of the laser in time. Now, as the pumping is being continued, the population inversion and in turn the gain also will build, and it will build slowly if the pumping is slow, and it will build rapidly, as you can see here, if the pumping is rapid. Now you know that the amplification of light is possible only when the gain exceeds the loss. If the gain is below the loss, then we know it very clearly now that amplification of light is not possible, because the oscillation of light inside the cavity is not sustained when the gain is less than the loss of the cavity. Now, what is where the loss actually takes place in the cavity? It essentially takes place in the by the partially transmitting mirror. See, you have your gain medium and you have put it in a cavity. One of the mirror is 100% reflective, the other is partially transmittive, through which you couple out the light that builds up inside the cavity, a part of it out, which is the useful loss forming the laser beam. Now this loss this transmission loss of this partially transmitting cavity is independent of time. It doesn't depend on time. And therefore, the loss, this is the loss, can be represented as a straight line parallel to the time axis in this gain curve. This is the gain. So loss doesn't depend on time, and hence it can be represented as a straight line parallel to the time axis. So this is the loss, which is represented as a straight line parallel to the time axis in this gain curve. Now commencement, when the lacing will begin? Lacing will begin at the instant gain crosses the loss line at this point. When it is pumped slowly, this occurs at a later time, and when it is pumped rapidly, the gain crosses or gain builds up faster, and therefore it crosses the loss line also early. Now at this point, oscillation, stimulated emission sets in, oscillation, amplification of light begins, so the laser pulse starts building up. So commencement of lacing thus begins at the instant gain crosses the loss line. Now stimulated emission, so you know, adds a photon to the system, but reduces the population inversion at the same time by 2. Let us appreciate this point. Say, this is your cavity. You have the active medium because you have pumped it, so you have gain has risen, and once the gain has risen, crossed the loss line, oscillation has begun, and light is actually growing inside the cavity as a result of to and fro oscillation of these photons, which has been initially this stimulated emission has been seeded with the photons which has been originated due to spontaneous emission. And you know now all these things quite well. But suppose we consider the two energy levels between which population has been inverted. This is the lower laser level, this is the upper laser level. Now let us just consider a situation where the lower laser level has, say, 4 atoms, 2, 3, 4, and the upper laser level has 10 atoms, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let us consider, say, one stimulated emission. There will be many stimulated emission which is happening, but let us just consider what happened with a single stimulated emission. So this atom is stimulated by these photons which are oscillating, and as a result, this atom comes down to the ground. So it now becomes this, and this atom has actually vanished, and instead it has now come down to the ground state. So then after this has happened, the population at the upper laser level is now 1, 2, 3, 4, 5, 6, 7, 8, 9, and the lower laser level is 1, 2, 3, 4, 5. And before this happened, the population in the upper level was 8 and the lower level 4. So in this case, the population inversion was 10 to the 10 minus 4 equal to 6. And now it is 10 minus 5 equal to 4. So the stimulated emission has added one more photon to this system. But at the same time, reduce the population inversion from 6. That means population inversion has been reduced by 2, while of course stimulated emission has added one more photon to this system of photons which are oscillating inside the cavity. Thus we can say now that the onset of stimulated emission sets up two competitive processes. Why? Because the act of pumping is trying to push the gain up. As we are putting energy into the system, pumping the system by putting more energy, this will tend to increase the gain, and stimulated emission pulls the gain down. So, act of pumping is trying to push the gain up, and stimulated emission is trying to bring the gain down. True, stimulated emission is also adding photons to the system, but at the same time reducing the gain. Now, as the number of photons rapidly builds up inside the cavity, as a result of stimulated emission, the number of photons are building up. And if the photons number increases, it also increases the rate of stimulated emission, because stimulated emission is proportional to the number of photons present. More number of photons means more number of stimulated emission, and more number of stimulated emission means you are pulling down the gain also at that increased rate, because each stimulated emission brings down the gain by 2. Thus, we can say that the rapidly increasing rate of stimulated emission would soon outweigh the effect of pumping and would eventually pull the gain down to the loss line. Because you are trying to increase the gain, but the stimulated emission rate, which is continuously increasing and increasing more and more rapidly, would eventually succeed in pulling down the gain to the loss line. And once it happens, thereafter, the gain will remain clamped to the loss line. Because imagine the situation that the you have just imagine you have slightly increased the gain to some extent. Once this situation has been attained, you are just trying to increase the gain. The moment you try to increase the gain, the stimulated emission rate also will increase along with the gain, because more photons will be generated. Then immediately it will try to bring the gain down. So once gain comes to the loss, it stays clamped to the loss line. This is called gain clamping. Gain clamping. So it will continue. How long? Until the waning of pump. You see, you are actually pulsing it. You are putting the pump energy in the form of pulse. So eventually time will come when pump energy will tend to reduce, as you can see here, which will eventually put the gain below the loss line. It has to happen. And once this happens, then this will put a stop on any further amplification of the intracavity line. If the gain has fallen below the loss line, there cannot be any more amplification of light as a result of stimulated emission. It would not be sustained. The oscillation of light would not be sustained. You now know it very clearly because this has been explained a number of times. However, the photons that are still present inside the cavity will continue to emerge to the partially transmitting mirror. Now, gain has fallen below the loss line. There cannot be any more oscillation. But already photons are present inside the cavity. So they will continue to emerge to the partially transmitting mirror. And higher is the transmission loss, faster will they emerge, and vice versa. Clearly, therefore, when energy is pumped into the medium rapidly, the gain will, however, the photons that are already present inside the cavity will continue to emerge through the partially transmitting mirror. Because you see, already light has grown inside the cavity and it was giving out this light. But when the gain has dropped below the cavity, there cannot be any more growth of light. But the light that was present inside the cavity will continue to emerge through the partially transmitting mirror. And how is the transmission loss? Will they emerge faster and vice versa? So then, clearly, how is the transmission? Faster will they emerge and vice versa. Clearly, therefore, when the energy is pumped into the medium rapidly, the gain will manage to rise to a higher value. Because gain rises at a faster rate, so before stimulated emission can actually beat it and pull it down to the loss line, that gain would have risen to a higher value compared to the case where it was pumped slowly. So if you pump it rapidly, gain rises to a higher value, and higher value of gain will be reflected in the higher output power of the pulse. Thus, you see that by increasing the rate of pumping, if you pump it faster, the gain rises to a higher value and it will eventually result in higher output power of the pulse. Therefore, by increasing the rate of pumping, you can increase the peak power of the pulse. Now, to understand this more clearly, let us consider this example once again. See, here we were pumping the energy. So in the example that we had shown, the CW laser was emitting at a power of 1 watt. Now by pumping it for half second, and then not putting any pump energy for the next half second, we were able to increase the power like this. So now we put this 10 joule of energy instead of half second, we put it in quarter second, 1/4 second. So now, here the power is 40 watt. 10 joule is being pumped in 1/4 second. So the power here is 40 watt. So then, because we are now putting more energy, more power, but same energy within 1/4, within quarter second, so the power will rise even more. And you put the next one here. So that way, as you increase the rate of pumping, in the first case you are pumping 10 joule in half second, in this case you are pumping 10 joule in quarter second. So your rate of pumping has become more, so you are getting more output power of the pulse. So by increasing the rate of pumping, you can increase the peak power of the pulse, but of course, how long can you go? It depends on the capacity of the system, how fast you can pump your energy. I think I'll stop here today. The next class, we will take up how you actually pump a laser continuously or in the pulsed mode.